done the thing sliding up problem. Let's now try to do the block sliding down problems. In other words, just for the sake of making things look natural, we'll now make this mass the big N, and this is my pulley, and we'll make this mass the small n. So therefore, the downward force is mg here, tension T is up, and the acceleration direction now is upward over here, which would mean the acceleration direction is downward along the incline over there. Okay? So once again, like before, we still have an alpha and everything else. So we have an alpha here, which means that this is now it's a small mg, it's big mg, and this piece here, alpha, is big mg cosine of alpha, and then downward along the incline, I'll have big mg sine. Okay? So nothing changes, excepting I've flipped the big M and the small m, just to remind us that this is the bigger mass. And so it's, although in reality it's not so simple as just a big mass, small mass, it's just that we should just keep in mind that the acceleration now has flipped direction, this is up and down. But just for the sake of intuitive convenience, I've made it into a big mass. So at any rate, as far as this guy is concerned, I have mg sine alpha. I certainly have tension opposing it because the string, if you will, is preventing the mass from freely sliding down, right? So sliding down slower because of this tension T. And because it's going down, now the friction force will be that way. It will be upward. It will have to be upward because friction always has to oppose what's happening. So as far as this small mass is concerned, T is winning, so I put T minus mg is equal to ma. Compare that with what I have over there. When the big mass is on the right and going down, it's mg, big mg, minus T is m. Now it is T minus mg equal to m. So the thing is flipped. So that's one very important difference that you must be able to pull out of these problems. So as far as this one is concerned, the winning force here has to be the downward force. So I look at it in the following way. I make big mg sine alpha going downward as my positive force. It will be opposed by tension, so minus T. It will also be opposed by friction, so minus friction, and this will be big M times the same acceleration A, which the whole thing is sliding down. Alright, so F friction, of course, doesn't change, although the direction of friction changes. The magnitude remains the same, except when you replace small mass by big mass, so it's mg cosine of alpha, because that is the downward force, which is equal to the normal force, and you multiply this, in this case, since it's moving, by mu k. By the way, if the thing were stuck, we would have used mu s. So keep that in mind, what I had earlier. I told you the difference between kinetic friction and static friction. So let me complete this equation, put that ff in there. So I'll have big mg sine of alpha minus t minus big mg cosine of alpha, and let me put the mu k here. And this is equal to big m. So this is one equation, and that's the other equation. Let me add the two equations just like before. So here I would write t minus big mg, sorry, small mg is equal to small m. Okay, so that's what I have. Now I'm going to add these two equations. Why should I add? I should add them because I can see a minus t here and a plus t here. If I add the two, I would get rid of t, which will leave me with only one variable, which is acceleration. So the best thing to do, the easiest thing to do to proceed forward is to add the two equations. So this is something that comes through intense practice. More practice you give yourself, more easily you know how to solve these various simultaneous equations without the least amount of work. So if I add the two, I would be looking at the following. I would have big mg sine of alpha, okay, minus t minus mu k. T goes away, so we can drop that. Mg cosine of alpha, okay, minus small mg now, because I'm adding both things. And on the right side, I have big M plus small m times A. So once again, I'm in a position to actually get A out there. So A is, now you see big mg has two terms. So I will take big mg common. And I have a sine of alpha. And I have a minus mu k. See, previously we had a plus sign. Minus mu k cosine of alpha. Okay? Minus small m g. And then downstairs, I have big M plus small m. So that's my acceleration of the whole system. And once again, once I have the acceleration A, I can calculate T, because if you look at T, in this case, T is going to be M times G plus M times G plus. So this is A, mg I already know, so that's my equation T. So this is how this thing is going to work. Let me just make sure that everything I showed you is okay. Yeah, everything I showed you is just fine. Let's do a much simpler problem for a change. Important, nevertheless, is we take a table, let's say, and at the edge of the table, we put in a fluid. Okay? And then what we do is we take two masses. Let's say this mass here is M2, and this mass here is M1, and both are connected by a massless string. So I have this thing being pulled to the right by this guy, and this thing being pulled up. So tension here like that, tension here. So this requires a little bit of thinking, just to be able to make sure that you set up the problem correctly, and we can ask what is the acceleration of the system. Let us say we are told that m1g, so that includes multiplying by g, is 375 newtons at the end of the day of force. Let's say M2 is given to be 22.0 kilogram. So my job is to find the acceleration of the system. What is the acceleration? I'm not being told in which way it is going. I've just been told that M1 is 375 newtons and M2 is. So let us say there is no friction. Okay, so we first assume there is no friction. If there is no friction, almost any force will make it move. So we can easily see that if we apply, if you put a mass here which exerts m2g, that's a big enough force. In fact, that's more than 0. So m1 is going to move to the right. So what we should be able to say then is that you can write. Okay, so you can write m2g minus t. Okay, is m2a, and we should be able to write that m1a is, because it's only being pulled forward, m1a I should be able to solve this problem quite trivially, because I can simply write m2g minus m1a is equal to m2a, right? So I should be able to write if I take it to the other side, I can write m1 plus m2 times a is m2g, which means a is m2g over m1 plus m2. And you can stick in numbers and calculate that. That's a very straightforward problem if there is no friction. Suppose there is friction, then what happens? Suppose there is friction. So, let's say if there were friction, what do we do? Well, let's see what happens. First of all, as far as M1 is concerned, since tension is to the right, I'll have a T to the right. I must subtract 1 from it, friction. Assume the system is moving, so I can write mu k and 1g, right? And 1g is going to be the downward force. Normal force then also will be M1g, so therefore the frictional force will be mu k times n, or mu k times m1g. So I have to skip a step. So this will be equal to m1a. So tension is winning, right? Tension is pulling to the right, it's going to the right. That's the picture we had in our head. So T minus the opposing friction force minus mu k m1g is equal to m1a. So that's one equation out there. The second equation would be m2g, which is going down, being thwarted slightly by the tension T, also having the precise same acceleration because the two systems are tied, and therefore m2g minus t is m2a. And once again, like we have done before, you can completely work this out. I'll skip a few steps. Just add the two equations, the tensions will cancel out. You have m2g minus mu k m1g equals m1 plus m2 times a. From that you can infer what the a must be. And a works out to m2 minus mu k m1 times g divided by m1 plus m2. Now, for the sake of sanity, let us just say what happens if I turn mu k off. If I turn mu k off, I go back to this problem, and I get the result that I should have gotten in this problem. So if mu k were 0, I go back to that problem. If mu k is turned on, then mu k basically reduces the value of the acceleration by a certain amount, which is the friction. So, alright, let's switch gears now for a little bit. And I will work on some problems for you guys. And these problems are those associated with circular motions. As you can see, when it comes to forces, I'm trying to do a variety of different things such that they can help you build up confidence about the various difficult problems you'll encounter. Now, unlike in other examples, you are safe if force equations are encountered all over the map, and so therefore there are a great many more instances where you are going to have to develop the capability to solve the force equations. So let's say you are actually holding, let's say, a piece of rock, and the rock is tied to a string, and you're holding the string at some point. So here is the string, and let's say here is the rock. And now you start to swing it. So as you start to swing it, the rock now goes around in a vertical circle, and we will try to calculate the tension that the string will have when the rock is at the highest point and when the rock is at the lowest point, let's say, for these two cases. So here you are swinging the rock, is a rock going around. And let's say we take two positions, position A, which is the highest point, and position B, which is the lowest point. Okay? And of course there is a string. So let us first evaluate the situation at B. Which is the lowest point. So at the lowest point, what will happen is as follows. You will see that there is a downward force which is the weight of the rock mg. And since this is a string with a certain amount of tension, here is the string, and the string tension will always be inward, right? Because you are holding it in such a way that the string leads the tension upward. This is also the direction, because it's going around in a circle, of centripetal acceleration A sub c. So that is your net force. Your net force that cannot be taken away is centripetal acceleration. Nothing can change it. That's the net force that's going to emerge at the end of the day. So what you have is the downward force mg, you have a tension force from the string upward. Since eventually the resulting force is inward, I will write this T minus mg equal to M AC, which is my centripetal force. Which means that if I were to calculate how much tension will be involved, if I take mg to the other side, it will be M times G plus A. So therefore, at position B, what you will have is the string tension would be the highest possible value. It will actually be the weight of the string along with the centripetal acceleration that comes around, which is associated with how fast you are rolling. Remember, centripetal acceleration AC, the formula is square the velocity over the radius r being the radius of the circle, and the velocity is the speed, or equivalently omega squared r, where v, the speed, is r. Remember we did these last week. So therefore, that's where that comes from. So the lowest point, the tension will be the highest. So what happens at A, the situation at A? That's also very interesting. These problems may look simple when I do it on the board for you, but actually these problems are mighty difficult. So you have to really try to understand and spend the time to absorb why it works out that way. In fact, you can throw a string and see what happens. You will sense that your hand feels the heaviest when the string is at the lowest point, because the tension actually requires the largest value, and this is where you feel lightest. So that's what will come out now. So over here, as you can see, the tension is also going to be inward. Centripetal acceleration is inward, and as it so happens, mg is also inward. So all the forces are inward. So therefore, on the left-hand side, I will be adding the two forces. So I'll be adding P plus mg, because both are inward, and both are in the same direction as the centripetal force, which is MAC. And therefore, naturally, if I want to calculate the tension would be m times the centripetal force AC minus the acceleration to gravity g. And this is the reason why you actually feel everything is light when the string is on the top. So pretty much the same thing happens if you actually travel over a pothole. As you go down and come back up, you feel heavier. And as you go over a bump, if you're going fast enough, at the highest point of the bump, you will feel lighter. So this is the phenomenon that we just are able to calculate over there. We have done a little bit of circular motion already, so I don't feel too bad about putting circular motion out for you. But let's go through a trough, and then let's go over the bump. So let us say that you have a big trough. You can think about this as one of those things that's going on in the Olympic Games. So here you are, let's say skateboarding, coming along, right? And then you are going down happily. Here you are at the lowest point. And then you are coming back up again. Okay? So let us see what's going on over here. Okay, so at this lowest point, you can imagine you are traveling in a circular trajectory, excepting this is a semicircle. So just like there, you have a full circle. Over here, you are traveling in a circular trajectory. So therefore, clearly, you have a downward force. Let's say your mass is m. So this is mg acting downward. And there is a normal force. The normal force is going to be acting upward. The normal force is being given by the ground or by ice surface or whatever it is that you're going on. And because you're going around in a circle, you cannot escape the clutches of the centripetal force. So there will be a centripetal acceleration also acting that way. By the way, the centripetal acceleration this time doesn't require a string, right? Over there you require a string. Now there is no need to have a string. Lower this one. So now you see, I should be able to set up the force equation. The force equation here would be n would be upward, same direction as the centripetal acceleration. So I should have an n. I should subtract off mg, so n minus mg, and that will be mass times the centripetal acceleration. So clearly, the normal force, which by the way is what you feel at your weight, is going to be g plus ac, which is basically trying to tell you that at the lowest point, as you come down, you will feel the heaviest, which is exactly what I said, the way you feel when you go over a point. Here on the other hand, you're going over what would be a hump, again, a part of a circle, and out here, let's see what happens to you. So there you are, and you'll be coming along. Now here, your mg is acting downward, right? The normal force is going to be that way, alright? And then your centripetal acceleration is also going to be inward. So now what you'll have is you'll have mg, right? mg minus n, and the downward net force would be the centripetal acceleration. So mg minus n is mac, and therefore the normal force that you feel is going to be, if I take to the right, bring that to the left, and rewrite it, g minus this. So this is the reason why, again, the normal force is the effective weight you feel. So therefore, as you can see, if the weight you feel on the ground is mg, now it will be mg minus mac, so you'll feel lighter. So as you go over a bond, you feel lighter. I should tell you that these are highly non-trivial. So this again is you feel heavier because the weight is what you feel. And this here is feel light. Okay? Feel heavier and feel light. Alright. So let me now talk a little bit about going around in a circular trajectory. This turns out to be an interesting and important problem, and most certainly something that you should expect to see in some way, shape, or form in exam 2. So let's say that you are going around a circular track. Here is your car. Okay, going around a circular track. You're going that way. So this is your center, and so there is a centripetal centripetal acceleration in this direction, okay? So now you have an energy going downward, and you have a normal force, it's flat ground, going up. So as far as things are concerned here, you have an mg and a normal force, and you have a centripetal acceleration that's inward. Now it turns out, if you try to do this on an icy road, right? So you're driving, let's say, 30 miles an hour, going around a circular bend, and it's icy. We know what happens. The centripetal force is trying to pull you in, but what's going to happen is that the road surface, because it is icy, is not giving you enough friction. The road surface is supposed to give you some friction. So if it doesn't give you enough friction, as you're making this turn, you tend to slide out. Okay? So, in this case, therefore, the motion is happening this way, along the circular trajectory. And if there is friction, you should not have any motion in the radial direction. This is the radial direction. But it turns out that if there is no friction, you will slide out. So therefore, the friction force that comes into play because of the rope, let's call it F friction. This friction force is actually balancing the centripetal force, which is mass times the centripetal acceleration. So in other words, it is trying not to slide out. So therefore the friction force is inward. It's trying not to slide out of friction force before. It's trying to prevent motion in this direction. So yeah, so friction force is going to oppose that. It's going to be inward. So this is what you got, and we know that the friction force here is the coefficient of friction times the weight, the normal force, and so that's going to be mu times mg. And this is going to be v squared over r, the centripetal force, or equivalently m omega squared times r. Okay, that's what we got. Now, there is something interesting in this problem, which is very easy to make a mistake on. As I told you, all the motion is happening in the radial direction. Sorry, along the curve of the circle. There is no motion happening in the radial direction, which should be this way. In fact, if you're moving this way, you are skidding. So friction is trying to stop you from skidding, but you're going around the circle, and that's the only motion that's happening. There's no radial motion that's happening. So if there is no radial motion that's happening, the friction as far as the radial direction is concerned, this direction is concerned, if there is no motion in the radial direction, then you must remember that this is static friction and not kinetic friction, even though the car is moving. Okay? The car is moving like this, but the car is not skidding outward. So therefore, as far as the radial direction is concerned, so it doesn't skid outward, you are talking about a static coefficient of friction. So it turns out then that the static coefficient of friction can be calculated, for example, or you can find out what static coefficient of friction will sustain what speed. So I can write us times mg equal to mv squared over r. Okay? The m stands out. Curiously, the mass of the car doesn't matter. So whether it's a truck or whether it's a tiny little Fiat, it doesn't matter. And therefore, us is going to be equal to v squared over r, which means the maximum speed you can sustain. Oops, I lost a g somewhere. V squared over rg. So the maximum speed you can sustain is going to be s times rg squared root. Okay? So if you know the s, if you know the friction coefficient, if you know the radius of the circle isn't too tight. If the circle is too tight means that the radius is small. If the radius is small, you cannot sustain a high speed. So therefore radius is going to be large, s is going to be large, g is what it is, and that sustains a certain speed. So therefore the speed limits that you will see on various kind of hairpin bends, if you're doing mountain riding, are typically dictated by us and r. And they're typically a fairly fixed number. They can say 15 miles per hour or 20 miles per hour and no more. And that's because it's coming from this kind of a simple calculation of the first instance. So that was the case of a flat surface. So if I were to draw the force diagram in a somewhat different way, I would have drawn, this is the centripetal force, mass times the centripetal force acting inward. This is going to be your mg. The normal force on the car is upward. And because the tendency of the motion would have been to go that way, to avoid having any radial motion, the friction force must also be this way. So that would have been the force diagram. So that's friction force equals MAC. These two become equivalent, and mg is equal to n, and from that you work out the entire relationship, because friction force is mu s times n, so mu s times mg, and so on. Okay? So just to be sure, this speed, by the way, is the maximum speed you can sustain without skidding. Okay? That's not any speed. That is one maximum speed you can sustain without skidding, and that is dependent upon µs, because remember, µs itself is the maximum friction force. We discussed that in the very beginning today, and times r times g. So let us say you are actually driving on ice. So in other words, suppose you don't have friction. For instance, what you have in all these luge competitions and so on. They are going on ice. You have very, very tiny friction. Not the kind of friction that's going to sustain stable motion. In fact, any kind of stability as you move in the radial direction, to be specific. So let us say, again, you are taking this circular track, but now, because there is no friction, as you would again see during any kind of a luge type competition, for example, or even if you go to Daytona 500 or Talladega 500, you will see that the racetracks actually go high up like that. It's called banking, nothing to do with your actual bank, but it's called banking. So in other words, there is a certain plane at the surface level that is associated with this road, and that's called banking. But suppose this is your car, okay? This is your car. So let us draw a free body diagram. So this is the surface, and this is your car. So therefore, you will get a normal force from the surface, and let us say this is the direction of the normal force. And obviously, since you're going around the circular track, there is a centripetal acceleration inward. So I should now be able to draw the force diagram. I have a normal force going that way, right? Mg is always vertically downward, and I have, this is the vertical direction because mg is downward, and let us say that this angle here is theta. Observe how I am drawing the angles. So n is that way, that's this way, mg is vertically downward, right? And this angle here. So clearly, I can immediately see that n cosine of theta, which would be the vertical component of n, must be equal to mg. So that's an equation that I can immediately get by staring at the free body diagram that I have drawn. So n cos theta is equal to mg. And I should also be able to then resolve something in this direction, which would be my direction of the radius. By the way, this I should draw a little bit more clearly. So this is the inward direction. So this is n sine theta, obviously. And this n sine theta is also the direction of the centripetal force. So therefore, I should write n sine theta is equal to the centripetal force mass times a sub c, mass times v squared over, let's say r, where r is the radius of this. So So that's what we got now. Now, so we have two equations then. N cosine of theta is mg, and n sine of theta is mac, which is mv squared over r. Now, let me just tell you, from this point on, if you see an n cosine theta or something like, f cos theta or something or so and so, and f sine theta or so and so, you should always consider, you should have the urge to see what happens if I divide one by the other, because then I can get into this variable. So I can write n sine theta divided by n cos theta. Now that's pretty good, because that's a tan theta, and we know how to calculate tan theta, because we know how to calculate sine theta and cos theta. So over here, n sine theta will give me mv squared over r, and n cos theta will give me mg. So therefore, I should be able to write mv squared over r times 1 upon mg. So m's will cancel out, n's will cancel out, which would give me tan of theta, right? The sine theta by cos theta is a tan theta. And then tan theta would be v squared over rg. So therefore, if you want your motion to be stable, you're going around in a circular track and be stable, you want to make sure that your angle theta is correct. So this angle theta is therefore going to depend upon the radius and what are the highest speeds that you want to sustain. And you will see that if you want to sustain speeds of hundreds of miles per hour, this angle theta must be pretty close to 0 actually, because this is going to be almost like vertical. Almost like a 90 degree, because then what will happen is that the slope is going to be like this, so therefore n would be like that, and therefore the angle with the vertical, which is this theta, would be going towards 90 degrees. Okay, so that's what happens. If you want to sustain a very high speed, then this angle theta is going to be near 90 degrees, and we know that sine 90 is 1, cos 90 is 0. So as you approach 90, the value of tan of 90 will begin to become an extremely large number, going to infinity. So therefore, theta has to be sufficiently large to be able to sustain a high enough speed. But almost any speed can in principle be sustained in this case. By the way, in all the considerations in this problem, we have actually not used any friction. So the stuff here works out without any friction being involved. Alright. I can probably go on, but at this point I will stop, because now the stuff that's coming up is gravitation, and I do not think that I want to start gravitation with about half an hour to go, because it's quite a bit of stuff that's coming up, and then I have to get into the concept of work done. The basic idea is that it feeds off the centripetal force work I've done, where essentially I have two masses, and the masses attract each other by a universal force called gravitational force, and one can actually study this gravitational force by a variety of ways. And historically, a great deal was learned about the gravitational force by looking at the planets. These were the early measurements done by Tycho Brahe and Nicholas Copernicus, who was Tycho Brahe's assistant, and Johannes Kepler, who was Tycho Brahe's assistant. So Kepler and Tycho Brahe, they worked out by observing the planets they could see with the telescopes in those days, in the late 1400s or whenever it was, to figure out how long it takes for those planets to go around the sun, and having an estimated idea of how far away they were, and then trying to figure out why they were going around the sun the way they were. And the idea was that the reason why they were going around the sun was because the sun was attracting these planets by gravity. So if the planets were not moving, they would just collapse into the sun. But because they're moving, they're able to sustain periodic motions. In other words, the gravitational force that is pulling these planets towards the sun, the Earth included, is being balanced by the centripetal accelerations. This concept is not super simple, but it's simple enough that I want to take a bit of time to tell you why the gravitational force equals the centripetal acceleration conceptually, and from that, what you can learn about the nature of the gravitational force, the nature of these periods, and so on. Gravitational force is a fundamental force, by the way, and gravity is everywhere. So in other words, any two masses, so if two objects have masses at all, those two masses are going to attract each other. Gravity never repels, it only attracts. So everybody in this room, everybody in this university, everybody in Buffalo, everybody in Western New York, everybody in the US, everybody in the world, they are simply attracting each other. And because people are moving around and their masses vary, the attractions obviously do vary. Do we feel this? So if I'm walking around here, do I suddenly feel attracted to you and move in that direction? The answer is no. Because gravitational attraction is extremely weak. Weak enough that our sensitivities are such that we cannot feel it. We cannot really feel gravitational attraction from another person. It's just too weak. We do feel Earth's gravity, which is why if I jump off the window, I'm going to get hurt, right? So that's big enough, because Earth, of course, is an extremely large mass. It's 10 to the 24 kilograms. We are on the order of less than 100 kilograms typically, most of the time. So we are not even 10 to the 2 kilograms. So you're talking 24 orders of magnitude larger mass pulling me, and that I can feel, right? But even a very, very large mass like the moon is still not large enough to make gravity enormously important, because in the moon one can jump really, really high and gravity is pretty low. So I'll get into a discussion of gravity next. And when we get to midterm 2, we will indeed have gravity in the material that is covered, and we will have a little bit of coverage also on the concept of work done and work energy theorem, and I'll be assigning problems on these things as we go along this week. All right? Thank you very much.